Hey, what is up, AP Calculus? We're going to be covering a lot of things involving graphs of our functions and how we can use our derivatives to determine what graphs look like and the characteristics of those graphs for this whole unit. So let's just dive right in. It's going to be a lot of things, but hopefully it's not too hard to do. All right. So the first thing we're looking at is 5.1 extreme values of functions. So the extreme value theorem says if f is continuous on on AB, and notice this is a closed interval, right? Meaning that it has endpoints. So the brackets mean that we have endpoints. If they were parentheses, it would mean that we wouldn't have endpoints. We'd have open circles at the ends. So be very careful with this. With that small detail there. So again, if f is continuous on the closed interval AB, then it has a maximum and minimum. So pretty easy, right? If it's closed, if it's continuous, then it's got to have a highest value and a lowest value. Now keep in mind, even if it were a straight horizontal line, right? And it's closed, then it does have a max and a min. They're just the same value. Okay? So next one, we're looking at local extrema. So local extrema, we're looking for any tops of mountains or bottoms of valleys and also the endpoints. So if you look at our graph here, we have a local max at that top of the hill. We have a local min at that bottom of the valley. And while the absolutes are also considered local, that just means that that's the largest or smallest number overall. Notice we don't have an absolute min here because our graph has arrows, which means that it continues downward. Yeah, so if it continues, we can't find a value for the min. Okay, so how we use calculus to find local extrema is on the interior of our graph, so inside of our graph, between the two endpoints, right, we're looking for where f prime of x is equal to 0. So we find the derivative, we figure out where the derivative is equal to 0, and then that tells us where our local extrema are on the inside of our endpoint. So this one, right? Because also the derivative refers to the slope, right? So the slope 0 means that we're having horizontal tangents. So at these 2 points, the top of this mountain and the bottom of this valley, we'd have horizontal tangents where f prime of x is equal to 0. So we use our derivative to find where our local extrema occur. So critical points occur where we have our derivative equal to 0, or if our derivative does not exist. So we're going to check all those things when we're looking for local extrema. So let's go ahead and jump into this one. It says find absolute max-min of f of x equals x to the 2/3. And they're giving us the interval on -2, 3. So number one, let's locate critical points. So again, critical points tell us we need to do our derivative, and we have to find if it's equal to 0 or does not exist. So let's do x. The derivative, we're going to drop down to the 2/3, and then we're going to subtract 1 from 2/3, so that's going to be -1/3. So this is going to be f prime. Okay, now we have to figure out where is this going to be equal to 0, or where does this value not exist. So maybe let's do this just to make it a little bit cleaner when we're working with our values here. Let's change that -1/3 to the cube root of x. Okay, so we know that if I plug a 0 in there, right? So x equals 0 would be a critical point. Because if I plug 0 in there, then the denominator is going to be 0, and we'd be looking at a location where our derivative does not exist. And we know that anything else we plug in here should be good. So what we're going to do is locate critical points. So we got to have a critical point at x equals 0. We're also going to check the endpoints too, right? So we have -2 and 3. Okay, so we're going to plug our values in there and see what happens. And then we're going to determine the absolute max or min. So let's change colors. So we're testing these 3.0, -2, and 3 into our original equation. So x to the 2/3. So let's do f of 0 is 0. Okay. Let's do f of -2 is going to be -2 to the 2/3. So that's going to be -2 squared is 4. And then the root is 3. So we have this, and then we have the last one, which is 3. So f of 3 is going to be 3 to the 2/3. Oops. All right, so 3 squared is 9. Okay, so the absolute min, right? So absolute min, the smallest number we get is 0. The absolute max is going to be the cube root of 9. Okay, so not too bad, right? We just have to decide or determine where our critical points are. We determine that by finding where our derivative is equal to 0 or does not exist. We also take the endpoints, we plug all those things in, and we find which one is the smallest and which one is the largest to figure out which is the absolute min and max over our interval -2, 3. All right, same idea here. This time they're not giving us an interval, so we're going to find it overall. So let's rewrite this first, right? Let's rewrite f of x equals 4 minus x squared to the -1/2, right? That's going to make it easier for us to do our derivative. Okay, so our f prime, then we drop down our (1/2), and then because of our negative sign, we're gonna, well, actually, this is gonna be, let's not skip this step then. Drop down our 1/2, 4 minus x squared, and we're gonna subtract 1 from 1/2, which is -3/2. All right, so let's rewrite this now nicely. So we have negative, 2 stays in the denominator, and put the 1 in the numerator, and then what this is going to become is going to be 4 minus x squared square root to the 3rd power. Right, the top is the power, the bottom is the root. Now let's figure out where this is going to be equal to 0. So anytime we have x squared, that's going to be, anytime we get x squared to be 4, that's going to be 0, right? The cube root of 0 is still 0. And then the 2 is going to be, it's not going to matter because 2 times 0 is still going to be 0. So we have 4 minus x squared equals 0. When is this equal to 0? Some of you can already figure it out, right? That's going to be at 2 and -2. But let's go ahead and solve it anyway. Oops. Minus 4. Okay, so we get x squared equals 4, square root, x equals positive -2. Okay, so what we need to do here is plug it back in to check our extreme values. But when we plug it in, we get 0 again, we get undefined. Okay, let me just check this to make sure we did it correctly. I'm pretty sure we did, but it seems weird that we'd be asked to find values and then they come out to be undefined. Oh, I see what we forgot to do. We forgot to chain. So when we did this one, we forgot to chain here. The chain here is 2x, right? Because we forgot to do the derivative inside. How silly of me. So then we do have an x on top. 2x. Let's clean this up a little bit. Well, all right, we'll clean it up a little bit. All right, so the 2 and the 2 cancel out. So we have the same exact thing, but we have the x on top. Okay, so we do need to check this, right? This is still valid, right? But we can't plug them in and get an answer, so we know those are out. So what we're going to do here is we're going to plug in the top, right? So we know that if I plug a 0 in here, that our whole thing is going to be equal to 0. So this is going to be one of the critical points. So we have critical points at positive, negative 2, which we already checked, right? If we plug positive or negative 2 back in there, then we just get undefined. So it's not going to work out. But also we found that 0. So let's go back and see why it's equal to 0 for those of us who might have missed it, because I think we just glossed over it really quickly. So we're taking our derivative, right? And we're setting it equal to 0. It doesn't matter what the bottom is, because when we multiply that bottom by the top, it's going to come out to be 0. So the only thing that we have to worry about is what makes the numerator 0 when we're trying to find our 0. And obviously, because it's just an x, then 0 makes x 0, and then our whole numerator is 0. So that's how we say our second critical point is at 0. So when we're talking about any rational function, we don't have to worry about the bottom when we're looking for zeros. We worry about the bottom when we're looking for undefined points. That's what we did here. If we're looking for when the function is equal to 0, we just worry about our numerator. Okay, so when we go back and plug in here, we're going to say that 1 over 4 minus 0 squared, square root, right, is going to be, well, 4 minus 0 is 4, square root of 4 is 2. So we should also be looking at positive, negative 1/2 as our extreme values. So the positive 1/2 would be a local max. The negative 1/2 would be a local min. Okay, so a lot of stuff to do here, but it's mostly because I screwed up the derivative. We forgot the chain rule. Don't be careless like I was, but the same idea applies, right? So because we're not over an interval, we don't have to worry about the endpoints, but we're on the interior points, we're gonna see where our derivative is equal to 0, our derivative does not exist. Plug those numbers back in and determine which ones are the mins and maxes. Okay, and on this one is a piecewise function, right? So they're defining f of x as 5x minus 2x squared when x is less than or equal to 1, and then x plus 2 when x is greater than 1. All right, so critical points. This one doesn't have endpoints, right? X is less than 1, it's going to continue all the way to infinity, or negative infinity. X is greater than 1, also it's going to be infinite, right? We're not going to have an endpoint there because it's going to continue on to positive infinity. So let's check critical points. Our critical points for each one of these is going to be, let's set them equal to 0. Or actually, let's take the derivative of it, right? So each part we're going to find the derivative of. So the top part, the derivative is going to be 5 minus 4x. Right? The second part, the derivative is 1. So we're trying to find when this is equal to 0. Well, the bottom is never going to equal to 0. This is a linear function. Therefore, it's not going to have any critical points where it turns from positive to negative or negative to positive. So we're not worried about this one, right? But on the left-hand side, 5 minus 4x equals 0, we can solve this algebraically. And then we get x equals 5/4. Okay, also when we have a piecewise function like this, we also have to check the place where they join. So at x equals 1, right, if I plug 1 into here, into the top, we get 5 minus 2, which is 3. And then if I plug it into this one, then I get 1 plus 2 is 3. Notice that they're the same point here. So what this looks like, well, we have this function, which is a parabola, all the way to 1. And then this function joins it out here. So we have this one that we already found at 5/4, right? That's the one from the parabola. And then we have this one here. Did I write this backwards? For x is greater than 1, maybe? Hold on. Less than or equal to 1. Okay, we're okay. And then we have one here. So the maximum here would be at 5/4. And then the minimum would be at 1. Minimum would be at 1. So at 1, our y value is, that's going to be a min, which is 3. Now, this is the thing that's kind of messing me up, because 5/4 is not less than or equal to 1, but in the book, they have it as less than 1. Did I do that weird? Five. Oh, it's because there's no x here. Sorry about that. So it's just 5 minus 2x squared. Therefore, the 5 would derive out. Then we just get negative 4x as our derivative. And then therefore x equals 0. That makes sense. Okay, so we have a max. This is at 0. And that value is going to be, if I plug in 0 into my top equation, then I get 0 squared. 0 squared is 0 times 2 is 0, and then 5 minus 0 is 5. That makes sense. All right. Okay, on the last one, this one we're doing graphing, so it says find extreme values of f of x equals ln absolute value x divided by 1 plus x squared. All right, so let's go to my strange rig up that I got here. All right, so we're just gonna input, well, let me do this beforehand so that, so you see what's going on. So ln, remember your absolute value is under math. Absolute value of x divided by, I'm going to put parentheses around there, 1 plus x squared. Okay, so let's switch to camera here. So I inputted it, so your ln parentheses, you're going to hit the math and then shift over to number to get to your absolute value. And just make sure that your denominator is in parentheses. So what we're going to do is we're going to graph it. My window's zoomed out, so I'm probably going to want to zoom in. So I'm going to zoom 6, which is standard. Okay, so it's asking us to find extreme values, right? So let's see if we can trace this just to kind of get an idea here. So we know that when x is 0, it's saying y is equal to blank, so we know it's undefined there. So we're not, well, our slope would be undefined there. It's discontinuous at that point, so we're not going to worry about that little dip in the very middle of it, right here. But what we're going to do is we're going to find the maxes in this area and in this area here. Okay, so let's go ahead and second calculate. We want to find the maximum. And we're going to set our boundaries here. Make sure you set your boundaries definitely to the left and to the right of those spaces here. So 1 to the left, 1 to the right. So negative 0.69, 3147. And let's do this side. Whoops. Calculate our max again. Set up our boundaries. And it's at the same point at 1. So at 1 and negative 1, we find that we have the same maximum values, negative 1.693. Okay, so let's go back here. 1 and negative 1. So we have maximums at those two x values, right? 1 and negative 1, and we found that the value is going to be negative 0.693 for both of them. Okay, so you can use your calculator to find these values, but we also want to be able to do them using our derivatives. We're going to be continuing on with this extreme value theorem stuff. Actually, we're done with extreme value theorem. Next time we'll be talking about mean value theorem. All right, good job.